So example 1.4, or notes 1.4, example 8. Yeah, now, maybe I shouldn't give you the name or give you kind of the takeaway right away. We should kind of analyze it first and then work towards that goal. So here's one. You have the limit as x goes to 0 of a ratio of two things. Never not first. Ever never not first. Plug in a 0. What do you get? You get 1/2 minus 1/2 in the top, which is 0 over 0. Now 0 over 0, of course, means the function's undefined, but the limit will. So 0 over 0 is also now a cause for celebration, right? Hooray! Hooray! The problem is not over. In fact, the problem is just beginning, right? We are just arriving at the amusement park, not leaving at the end of the day. There's a whole wealth of fun to be had. Who's the bad guy in the bottom causing 0? X. Okay, let's see what we know already. We have two terms in the top. Do they both have an X factor? Yes. No, they don't. So it's not a factor and divide out. Ratcon. It's fun to say. Will it work here? Not really. We don't have any radicals to rationalize. Although we do have two terms. If you tried multiplying by the conjugate, yeah, messy. Okay. So what else? Well, yeah, we can what? We can factor out 1/2. 1/2. Yes, so the X is alone. Yeah, let me rewrite this in this format, which might make it a little bit uglier, but then also more recognizable. This is a complex fraction, sometimes called a compound fraction, which sounds painful, right? A compound fracture. This is a complex fraction, and there's really no way to eradicate the 0 from the denominator, but maybe intuitively you might try eradicating the complex fraction, because complex sounds hard. Getting rid of the complex part should make it easier. And there are several ways to do it. Back in little school, you probably learned to get a common denominator in the numerator to get it as a single term and then stay, change, flip, right? But this is not little school, so we are going to learn a more efficient way to do it. The quickest, fastest, most effective, and fun way to eradicate a complex fraction is to multiply by a clever form of 1. That is the LCM of all your miniature denominators, for lack of a better term. These are what I call the miniature denominators, okay? 2 plus x, or x plus 2, 2, and 1. What's the smallest multiple that all of those go into? Not the greatest common factor, but the least common multiple. 2 times 2 plus x, or x plus 2. Yeah. Generally, you're going to take at least one factor of each type. And if one of them has two factors, you have to take that. So you take the largest representative of each factor type to get the LCM. And, of course, 1 doesn't matter. So 2 times 2 plus x in the top and 2 times 2 plus x in the bottom. So we really just multiplied by 1. Now, here's how it works. The limit as x goes to 0. Remember, I'm writing it first. You're going to treat this as an upstairs-downstairs problem now. So the 2 times 2 plus x up there, really, it's like over 1, okay? But you don't need to write that because y'all are good calculus kids. All you have to do is distribute this factor group to the first term. And because it's over 1 from high to low, what's going to happen with your 2 plus x and 2 plus x? They divide out. They're gone. And you're just left with this 2 times the numerator over there, which is 1, which is just a what? A 2. And then you're going to have the minus sign. And then if you distribute this factor group to the next one, what happens with your 2's? They divide out. And you're left with 1 times the quantity 2 plus x, which is just 2 plus x. Error alert, error alert. What did I do? I forgot to either distribute the negative or keep the parentheses intact, and that is a very common error. So make sure you do one or the other. Y'all are probably to the point where y'all could distribute the negative. But that takes care of that, and then in the bottom we just multiply straight across 2 times x times 2 plus x. And do we want to expand the bottom out? Do we want to do that? No. Because remember, our goal, never lose sight of your goal, is to divide out the factor of x. So if we leave that factored, we can divide it out. Now here's what some people do. They get real excited here, right? And y'all will definitely find the humor in this. Hey, look, the 2 plus x is divided out. But then the bad guy's still Yeah, that is wrong for so many reasons. We are not eliminating the bad guy. That's an innocent person. That's 2 plus x. We're trying to get rid of the bad guy. It doesn't work anyway. there's a built-in fail-safe against this, in this case, because 2 plus x on the top is starts with T, rhymes with term. It's a term. It's a term in the top and a factor in the bottom. We can only divide out common what? Factors. So that doesn't work. That's like an early mathematical mistake or a calculus mathematical joke. Okay? So what can we do? Well, we can distribute, right? We can expand it out. Now, I'm not going to write it all out because we can distribute and combine in our head. If I distribute the negative, I'm going to have a 2 minus 2. Oh, that's 0. And then what type of x? Negative x. And that's important because, again, that's the negative sign that some people tend to leave off. And that's important because you might end up with the exact opposite of the correct answer, and I can't think of a bigger way to be wrong than to be the exact opposite of something. Okay, so all we did is we eliminated the complex fraction. Can we accomplish our goal at this point of eliminating the bad guy? They divide out, leaving a what in the top? A -1. And if you want to help yourself, put a -1 there in parentheses so you don't miss it. And of course, once the bad guys are gone, all of these roads lead back to direct substitution, or the world is safe once again for democracy, however you want to look at it, whatever analogy you're following. Plug in a 0 for x, and you get -1 over what? 4. So -1 over 4. So the function, the original function, has a hole at the point 0, -1/4. So this one, I just call LCM over LCM. For years and years, I called it LCM over LCM until Chase Waldrop was in my class last year and decided that it's better to call Lickum over Lickum. So it's become Lickum over Lickum. Okay? So what are we doing with the bad guys? We're licking them. Licking them good. I guess. I don't know. LCM over LCM. The names aren't that important. It's kind of fun to have a name, but you're just eliminating the complex fraction. That's the obvious math that you're going to do when you see a complex fraction. Okay, letter B. The limit as x goes to 0 of x over that. That looks like a complex fraction because it's written in the horizontal bars, not the slant. But let's plug in first. Let's plug in a 0. We're going to get 0 on the top and 1/6 minus the 6. That's 0. Alrighty. 0 over 0. Are we sad about that? Heck no. Heck no. The park is open, right? Let's go. Complex fraction. Maybe eradicating the complex fraction will work. What's the LCM? 6 times x minus 6. Now, if you can't get the LCM over the LCM, a CM will work. If it's not the least common multiple, if it's just a common multiple, it should work. You're just going to have to do more simplifying. All right, so in the top, it's just going to be 6 times x minus 6. Who's the bad guy, by the way? At the factor of x, yeah. And on the bottom, good things should happen. You distribute, and your 6's divide out. So you're left with x minus 6 times 1, which in this case you could drop the parentheses because it's first. And then you're going to have the x minus 6 dividing out, and you're going to be left with plus 1 times 6, which is plus 6. Yeah. Now, if you don't want to write a whole other line, what's happening with the 6's? They're canceling. Good. And after they cancel, not before, but after they cancel, what happens with the x's? They divide out. Perfect. It has to be in that sequence. And then once the bad guys divide out, you can use direct substitution. So any x that remains becomes a 0, and you get negative 36. There you go. LCM over LCM. When you get 0 over 0, then you have a complex fraction. If you have a complex fraction, you plug in and you get 5 over 2, what's the limit? 5 over 2. Good. Yeah. So the new methods are retcon, 0 over 0, and you have 2 terms, at least one's a radical, and Lickum over Lickum, which is when you have complex fractions. All right, the next one I just call sledgehammer because of Peter Gabriel. Right, because of Peter Gabriel. That was the genesis for this nickname. No. It's called sledgehammer because, like a sledgehammer, we are going to beat the heck out of it. All right. A sledgehammer is a tool that pretty much anybody can use. Right. You don't have to go to sledgehammer school to learn how to use it, right? There is no operator's manual that comes with the sledgehammer, right? You just pick it up and do what? You start sledging, right? You swing it. And it does a lot of damage, but you can do it with unskilled labor, okay? So you're expanding things out. When you sledgehammer something, it usually shatters and breaks into smaller pieces. And so I call the sledgehammer method the case when you get 0 over 0 and you have to expand something out. Okay, so it works well when there's some obvious math to do, like distributing or expanding, like this one here. Now notice in this case we have the limit as h goes to 0, but we also have x's and h's in our expression. Which one are we treating as the actual variable? H. The limit defines the variable when you're in the process of evaluating the limit. So we'll treat x like a constant to start with. So let's plug in a 0 for h and see what we get. We get x squared minus x squared, which is 0 over 0. Hooray, hooray, hooray. Who's the bad guy? The factor of h. There's two terms in the top, neither one have a factor of h. There's no complex fraction, there's no radicals, so what to do, what to do? Foil, right. So we hit this with like a little 3-pound sledge, right? Dink. And that means we're going to expand that out. So that's what the sledgehammer is. The limit as h goes to 0. And of course, we know how to expand a binomial squared very quickly. Square, multiply, double, square. So square the first, multiply them, and double, you get 2xh. And then square the last, you get h squared. And then you have minus x squared all over h. If you were in pre-cal last year, this looks a whole lot like what Mrs. Lincoln maybe called my favorite problem, or what I called my favorite problem. The pre-cal kids learned it today, and it's going to be on their test tomorrow. My favorite problem. Yeah. So anyway, what's going to happen if we expand it correctly? Yeah, if our goal is to get rid of the factor of h, then everything without an h in it should cancel, which means that we could then factor out an h from all that remains, 2x plus h all over h. It divides out, and then we plug in a 0 for what's left, and we end up with 2x. Now, what we just did is we evaluated what's going to be known as the definition for the derivative. It's going to be known as the derivative of the x squared function. And the power rule would tell us that the derivative of x squared is just exponent times coefficient, which gives you 2, and then subtract 1 from the old exponent to get your new exponent, which would be 1, or 2x to the first. Okay? But we just derived it the long way. So that's coming in the next section. We'll not only be evaluating this, but we'll be setting these things up and then evaluating them. Okay? And you'll get what this means graphically if you don't already. Okay, so 2x, that's the answer. Once we get back to this point here, whatever we're going to be using this for, we could treat x as a variable again. But we treat it as a constant all the way through because the limit was h going to 0. So that was a little tiny sledgehammer. We expanded it out. This one here, maybe a 5-pound sledge. After we do what first, Peter Bain? Never not first. Plug it in, right? Because you're going to get so used to just recognizing something and doing something, I will trick you and I will make a direct substitution work. X squared minus 2x plus 1 minus x squared minus 2x plus 1. Anything minus itself is 0 over 0. Hooray, hooray. H is the bad guy. We have lots of factors in the top. Let's expand it all out. Okay? Slightly larger sledgehammer. H is our variable. So square, multiply, double, square. Distribute, negative 2x minus 2h plus 1 minus x squared plus 2x minus 1 all over h. These problems should work such that anything in the top without an h should cancel. Make sure they do. Don't just assume that they will, because then you can catch a careless mistake. So everything that is left in the top has a h in it, and it can be factored out. So we get 2x plus h minus 2 all over h, divided out, plug in a 0 for any h that remains, and you get 2x minus 2. Now this one also has an h in it like the first one, so this one is also going to be the definition of a derivative of a function, And the function whose derivative this represents is x squared minus 2x plus 1. The derivative of that is 2x minus 2. And we're going to learn the shortcut rule eventually. Exponent times coefficient to get the new coefficient. Subtract 1 to get the new exponent. So x squared becomes 2x. Minus 2x to the first becomes negative 2x to the 0, or just negative 2x. And constants go to 0 because they have x to the 0. So that's coming up. Right now we're just practicing evaluating limits. Sledgehammer. All right, so far so good? All right. Now, here is a new parent function. Mr. Jump, or Jumpman. Jumpman, Señor Salta. We called him this as well, también last year. Hombre Trepador. He has many different pseudonyms, but I call him Jumpman. And he is the exception to the 0 over 0 rule. What does 0 over 0 mean to us right now? That the function doesn't exist there, but the limit will because there's a hole, okay? Jumpman is the exception to that. As you might anticipate, Jumpman has a what there? A jump, yeah. Let's meet him, okay? Jumpman is essentially this guy here. He takes on two physical identities. Either the absolute value of x over x, or he could be x over the absolute value of x. But here's what's important about it. He's a linear function over a linear function, and only one, has the absolute values. Only one, okay? The top or the bottom. Linear over linear. What we're going to do is we're going to sketch the graph and see what he looks like. And to sketch the graph, we're going to kind of decompose him, gross, into a piecewise function. So let me go ahead and look at this version of him, and we'll see what happens. Now, the reason we're going with the piecewise function is because we have to kind of pretend like we're little computer programmers, and someone doesn't know what the absolute value of x does. So we're trying to tell a computer what to do when it encounters the absolute value symbol. So let's go ahead and start with the following. If we start off with positive x values, that would be like the start of your program. If x is greater than 0, then how do we take the absolute value of a positive number? Same thing. We just take it as is. So we could just drop the absolute values in the top. It's still going to be over x. And, of course, then we can simplify. What's x over x? 1. Okay? So you would write the program. If x is greater than 0, then let the function equal 1. Else, you could say, or in this case, if x is less than 0, how do we manually take the absolute value of a negative number? You multiply by negative 1, or you take the opposite of it. So it would be the opposite of x, or x times negative 1, and then over x in the bottom. But, of course, then that would simplify to what? Negative 1. So it's negative 1 when x is negative. Now, what x value have we excluded there? 0. Can we include 0? Not in this case because it gives you division by 0. So this is a real easy piecewise function then. It's 1 to the right of 0 and negative 1 to the left of 0. And if you want to sketch that, it looks something like this. Here is 1, here is negative 1. It looks like this to the left, looks like this to the right. It's two horizontal lines, and it jumps from positive 1 to negative 1 at x equals 0. Did I do that right? I did that wrong, didn't I? I did that wrong. That would be negative Jumpman. Yeah. Let's do this. I went right through my 1 and right through my negative 1. I'll do that over here. There we go. That looks better. That's right. When x is positive, we get positive 1. When x is negative, we get negative 1. So there's Jumpman. So in this case, what happens if you try to evaluate it at 0? You get the absolute value of 0, which is 0 over 0. And, of course, there's not a hole there anymore. There's a jump. So in this case, 0 over 0 means a jump. Now, what's important then is how are we going to evaluate limits at 0? Well, let's take a look then. What would the limit from the left of 0 be? It's negative 1. It's negative 1 everywhere. What's the limit from the right of 0? Positive 1. And what's the general limit at 0? It's got to be DNE. Good. Good. So is there a way to figure that out if we didn't know what the graph looked like? Yes, there is. And here's how we could do it. If we know that Jumpman is just going to consist of two horizontal lines, symmetrical to each other, one's -1, one's +1, and we're not sure if it's positive or -1 from the left, knowing that it's the same y value everywhere to the left and right, which will also end up being the limit value, you could choose any value to the left of 0. What's the value to the left of 0? -1. Just direct substitute a -1 in there. The absolute value of -1 is 1 over -1. What's 1 over -1? -1. Will it work if you plug in like a -10? Yeah. The absolute value of -10 is 10 over -10. 10 over -10 is -1. Same thing from the right. You can use direct substitution. So how about this one? What would be the limit as x goes to 3? 1. How'd you get that? 3 over 3. Yeah, direct substitution. The absolute value of 3 is 3 over 3 is 1. Okay? So for Jumpman, the y value on either side of the jump everywhere is the same as the limit value from that side. Everywhere to the left and right of the jump. Why is that important? Because now we have example 11. The limit as x goes to 5 from the left of the absolute value of 2x minus 10 over x minus 5. Never not first, plug in. What do you get? You get 0 over 0. Good. You get 0 over 0. Now, hopefully, at this point, you recognized Jumpman in disguise, or maybe he's a family member of Jumpman. You have a linear function with absolute values over another linear function. And we're approaching the value that gives us 0 over 0. So what that means is we're approaching the jump. And because it's a one-sided limit, we're coming in on a horizontal line, and the limit will exist, and we just need to find the y value. So what do we know? We know that anywhere then to the left of 5, it's going to be the same y value that is also the limit. So pick any value to the left of 5. 4. Plug in a 4 and see what you get. You get an 8 minus 10, which is -2. The absolute value is +2. And you got to plug the same number down here because it's the same x. 4 minus 5, -1, and so that equals -2. Yep. What about from the right of 5? Plug in a 6, right? Now, if you know that it's -2 from the left of the jump, it should always be at the symmetric value from the right. But if you were doing it brand new, plug in a 6. Actually, I'm going to plug in a 10, just because I like 10. 20 minus 10 is 10. The absolute value of 10 is 10. All over 20 minus 5 is 10 minus 5 is 5. Whew. Thank you. I didn't plug in a 20. That's 2. So it's the same thing. Now let's see what we could do here. This is actually a transformation of Jumpman. I want to show it to you very quickly. If I let f of x equal that function, I can factor a 2 out of the absolute values without any problem. Factor a 2 out on the inside, and of course the absolute value of 2 is 2, so you can pull it to the outside all over x minus 5. So this is a transformation to Jumpman, right? Jumpman looks like this. There's 1. I'll do it right this time, and there's -1. What, first of all, does multiplying any function by 2 do to it? Any function. 2 times the whole thing makes it vertically stretched by a factor of 2. So instead of 1 and -1, we're stretching it by a factor of 2. So now it's 2 and -2. And of course, what does replacing x with x minus 5 do to any function? Shifts it to the right 5. So this jump now is happening over here at 5, and it's 2 to the right and -2 to the left. So if you know what the graph looks like, you can answer it. But again, you don't have to. That's just a lot of extra work. If you know it's Jumpman, linear over linear, one of them has the absolute value. If you're approaching the part that gives you 0 over 0 and it's a one-sided limit, pick any number from either side. Okay, now, if you're faced with the general limit and you plug in and get 0 over 0 and you know it's Jumpman, what can you say? D, N, E. Fantastic. So Jumpman is the new parent function, okay, and its transformations. All right, so example 12. Jumpman likes to party, as you can imagine. So he doesn't like to hang out by himself. Sometimes he gets together with some of his friends. Like here he is with x squared. What's up, x squared? Let's try direct substitution. We're evaluating the limit from the left of -3. You're going to get a 9. Got it. And a -6 plus 6 is 0. Absolute value 0 is 0. 0 times 9? 0. Okay, so I got a 0 on the top and a 0 on the bottom. 0 over 0. Ratcont, no. LC, no. Jumpman, you see Jumpman? Linear function, 2x plus 6, absolute values over a linear function. How are we going to evaluate that? Plug in a number less than -3, like less than the -3, so to the left, like -4. All right, so if I plug a -4 in right here, let's see what we get. -4 times 2 is -8 plus 6 is -2. The absolute value is 2. All over, plug in a same number there. -4 times 4 is -16 plus 12 is -4. Now, what do I plug into x squared? Do I plug in my -4 as well? Or do we plug in the -3? You plug in the -3. Here's why. Let's backtrack a little bit. You remember the property of limits we had in 1.2 that said the limit of a product is the product of the limits. The Jumpman plug in any number to either side trick only works on the Jumpman component, which is the linear piece over the linear piece that causes 0 over 0. It has to be linear, and it has to be the piece that causes 0 over 0. So really, this is two problems in one. Based upon the properties of limits, we can separate it like this. Now, you're not going to have to physically separate this as long as you're aware. This is an entirely separate problem now than that. And this works by direct substitution. So what did we get? -4. We got a 2 over -4 times, if you were just walking up to this for the first time, you would not plug in a -4. You would direct sub and plug in a -3 and get what? 9. Okay? That trick of plugging in any number only works on the Jumpman piece. So you end up with, what, that becomes -1/2, so -9/2. So be cautious of that. So having said that, you give this one a try. Letter B. Or are we going to run out of time? Let's do it together because we're going to run out of time. Okay, we've got a couple minutes left. We're approaching 6 from the right. Plug in a 6, you get 36 minus 48, which is -12, plus 12 is 0, right, over 0. Yeah. 0 over 0. Do you see Jumpman in there? Where? Here's the Jumpman linear piece in the bottom with the absolute values. The numerator is not linear. Crap. It's not linear. But guess what factor is hidden inside there that is linear that's causing the 0? X minus 6. So we're not going to have time to finish, but tomorrow we'll pick up right here. You have to factor it and isolate the linear piece causing the 0. And then you do the Jumpman trick, and then everything else falls under previous rules. Okay? So be working on the worksheet. I think it's a pretty dang good one. I think there's many pages and a lot of practice opportunities. So we'll see you tomorrow. No quiz tomorrow. No quiz tomorrow. Just more calculus fun. Have a good day.